Good morning, ladies and gentlemen. Welcome to our course, Advanced Quantum Mechanics. I'm really excited to start it again. I give it already for a number of years. It's first time it goes online version. I mean the first lecture course. Right. The rule says that usually I ask you to mute your mics and questions you'd better put into chat, right? But if you feel your question is not answered, whatever, it can be miscommunications. So I could just plainly miss chat window. So please, in this case, unmute yourself, speak up. I will be delighted to hear you. Right. Let me first introduce myself. I am the lecturer. Yulia Nazarov is my name. We are team of 4. There are 3 other instructors which will help you with me along the course. Let me spend some time on organizational methods because, they say the course is difficult. I'm not sure it is true, but what is really difficult is the structure of the course. It's rather complex. Let's go for that. Right, first of all, we will have lectures. We will have 12 lectures. They are largely based on a book of myself and my former student, who also did advanced quantum mechanics and was instructor in advanced quantum mechanics many years ago. There is a book, perhaps you know from your student union, perhaps you could purchase these books, but well, you don't have to. So there will be lectures. Sometimes students kind of find it a little bit old-fashioned that I follow the book, but there are many reasons to follow the book, and the book, people say it's quite instructive. Good, that's a traditional part. And that will usually happen on Thursdays, like today. There are also problem-solving sessions, and there will be different activities. There will be presentations by instructors on more technical questions, more specific questions in comparison with the lecture material, kind of to help you with technicalities perhaps, or to refresh some of your skills. Besides, we have homework. Homework you do kind of alone, but we also have sessions of supervised homework. What does it mean in practice? In practice, we kind of gather in Zoom. I read formulation of the problem. You begin to think, and then you put questions to the chat. Then an instructor would open individual chat window to talk to you. It goes like this. There will be sessions about explanations of homework, naturally. And we are ready to answer any questions of you. Just give, let us know your questions. Let us know what to discuss in the sessions. We will always find time for that. Right, that's about problem-solving sessions, but the activities do not end here. Besides, as many of you already know, there are student presentations. There's a number of problems to choose from, And it is described on a bright space how to do this properly. But first step is to form a group of 5, and this is a group to work on presentation. And of course, you could also chat about the course within this group. It's usually useful. All right, so I guess about 8 groups have been formed. But if I look at the class list, well, it's kind of always bigger than a real number of students, but eventually I expect 25 groups. Right, so please talk to your friends, form the groups. There's still much room left. If you kind of don't form the group by end of March, no, by beginning of March, then yeah, we will just distribute you randomly among the groups. That won't be that nice. Good, the groups. Again, there are more activities and homework. There are 10 problems, homework problems to solve by structure and often by difficulty. They resemble exam problems. Right, this is separated into 4 homework packages. So you have 4 deadlines during the semester to submit your homework. And appointment is that the homework counts for 15% of your final grade. Anyway, even without this 15%, it is kind of very useful to do homework because of examination, and there will be examination. The examination will come in 2 versions. Normal version is for people who have done presentations in the group of 5. Just to tell to everybody who listens to me, if you have followed the course last year or before the last, and you have done your presentation, it counts. Don't bother to do it this year, it counts. Then you don't have to join any group. Fine, but yeah, sorry, I was distracted. 2 versions of the example: easy version, okay, normal version for people who have done the presentation, and a little bit more difficult version for those who have not. So in principle, you don't have to do presentation, but then be ready for a more difficult version of the exam. Good, the exam. It consists of a problem, a rather long problem to solve, like for 1 hour and a half. The problem is separated into points, and you got a certain number of score points for each point. It's very structured. It is technical. You're required to do calculations and, of course, think about proper ways to solve the problem which is given. And the second part of the exam consists of multiple choice questions, and this is mostly about lecture materials. The answers to these multiple choice questions you can find in slides of our lectures. Good. I guess I've done with organization. Well, perhaps it's too complex to just learn it for a minute. But well, we will work with this. You will have time to learn. Any questions now about organization, or I guess I see question. No grades for presentation. It's interesting. Actually, we grade the presentations. That is been done after you do presentation. After your presentation, you get some remarks. You would have to change your slides to incorporate the remarks. So finally, presentation is ready. In this case, we grade it. But usually we don't tell students the grades, and they never ask. The presentation grade doesn't count into final grade. It just, response on your presentation skills. So you might not believe, but most students never care about their presentation grade. Does the homework also count if it won't improve your final grade? It always counts. Right, so the grade is separated into 85%, which you can earn by solving the exam, and 15%, which you can fill with your homework. Homework is individual. You can, of course, do it in the group, but you have to make individual submission. To make it kind of sure, the exams are not in the group. They're also individual. We have a good way to do it in Zoom, and I guess we will have time and energy to make also a kind of test exam this year to check if all online technicalities actually work. Right. More questions about organization? Okay. Where is the homework handed in? It will be on the bright space. Right, I will open a certain page on the bright space where you can submit your homework. Will the exam be open book or ensured this moment? Officially, it's not open book, but nobody would request you to close the books, right? You can kind of use all this, all information you can get, provided you do it alone. After the exam, there is usually a request for appointment. Right, we cannot make appointment with all students, but we kind of have a significant set, and then we just look at these at submitted exam papers and try to figure out whether student did it him or herself or with the help of others. Okay, let me be frank about this, right? If there are any doubts, the case is suspended. Not that I love this practice, but that's what we have to do according to general regulations about exams. It is, yeah, at the moment we can think of online exams only. So the exam will be online. Will let's see, when will the homework be released? Okay, the homework of corresponding package will appear when we have enough lecture material to start with. That's usual practice. So I guess for first package, the homework will appear after the third lecture. Let us see more questions. Book from FFTP. Okay. I don't know. In principle, believe me, you can live without books. There's enough lecture materials. You can always ask questions. So I think you will survive till the end of March. Fine. Then, well, let me go further. Let me explain something about this course. Right. So first, about topics of this course, it is a little bit different from usual courses of advanced mechanics, which are taught at many universities. Usually, at that case, they go to field theories, to theory of elementary particles. We don't, because we are in Delft. We are in the capital of quantum technologies. And our quantum mechanics is, okay, we are Fitzmarkers, we are engineers, we are people who know how to fix the bikes, right? We don't go for field theory. We go for rather practical advanced quantum mechanics. But of course, there's overlap with conventional courses, and the main topics is the second, quantization, creation, annihilation operators for particles. We will go through condensed matter examples, not from elementary particles, condensed matter. We will talk about radiation optics, also is a conventional part, and some more advanced part, more modern part. We will talk about dissipative quantum mechanics, and this is seldom taught at the university's interesting topic. There will be a couple of lectures about this, and there will be only one single lecture about usual stuff which is taught at many universities about a relativistic quantum mechanics. I wanted to skip it, but my colleagues kind of insisted that students in modern days have to look at Dirac equation at least one time per life. So I keep it, but it's in line with all other presentations. Those are topics, and it's interesting interference with Windows. And there are 12 lectures which are separated by topics. Let me just, not to talk much about this, let me just say that this lecture, first lecture, we don't go any advanced, we just refresh quantum mechanics, which you're supposed to know, usual quantum mechanics, just to make sure that we have tools, that we have a tool set to do the job of understanding of these advanced topics. Fine. So let me start with overview of today's lecture. Right. Okay, we refresh quantum mechanics, but we start with refreshing classical mechanics. Quantum mechanics, in fact, is no independent theory. It is kind of, how shall I say, something which is based on classical mechanics. No new parameter except Planck constant. Good. And then we look at Schrödinger equation. Recall that for a single particle. We will recall Dirac formulation, matrix mechanics. Then there will be a piece of new material, but well, I'm not sure whether it's really new. There's a book with a cat, which I guess all of you know, which was your basic book, right? And even in this book, there's something written about Schrödinger and Heisenberg pictures. It will be useful in the course. We will talk about this. Right. And then some tools used in quantum mechanics, like perturbation theory. Most problems, exam problems, will involve this perturbation theory to some extent. Then we look at example problems of quantum mechanics. We will look at the qubit and harmonic oscillator, two very basic example systems of quantum mechanics. Then in the end time allows, I will talk about density metrics, about opposition of quantum description by a wave function and by a density matrix. Fine, this is outline, you're prepared. Let's go for a roll. It really looks like that windows which are opened in Zoom behave differently with each new Zoom version. Much of the progress. Right, we will talk about Schrödinger equation soon. We will write it soon. Oh, I'm sorry. I guess sorry. I have to start with first transparency. Classical mechanics of a single particle. Let us recall what is that about. There is a single particle and its state is completely characterized by 6 numbers. What are the 6 numbers? 3 components of its momentum, 3 components of its coordinate. What is special about quantum mechanics is that if you know these 6 coordinates in initial moment of time, you can compute, predict, whatever know, you can know the future. The concept of classical mechanics is a full predictability, what is called determinism, of all variables which characterize the motion of the particles. Good, what are these evolution equations? Time derivative of momentum is force acting on this particle. That force depends on coordinates, usually a particle in some potential. So it's a gradient of the force. And the time derivative for coordinate is the velocity. So for non-relativistic particle, it is p divided by m. Those are equations. Those are set from your own studies of quantum mechanics. You might recall that there are many ways to come to these equations. As one can just postulate them as Newton did, or one can derive it from Lagrangian or whatever minimum action principle. We will recall one of many formulations of classical mechanics, which is called Hamiltonian formulation. In this case, one has a function, Hamiltonian function of coordinates and momentum, right? And equations in general are made as follows. Derivative of momentum with a derivative, time derivative of momentum is a derivative of the Hamiltonian function with respect to r, and it is a swap if you look at time derivatives of coordinates. All right. Good. One can take as a standard Hamiltonian function. It contains kinetic energy, potential energy. And if you do this little algebra, you just come with these equations. What is handy for general Hamiltonian, again, utilizing these equations, one can prove that time derivative of the Hamiltonian function is 0. What does it manifest? It manifests energy conservation. The Hamiltonian can be associated with the energy of this particle. Fine. Particle, 6 numbers, full predictability, Hamiltonian function. If you take many particles, it's almost the same. One has to take into account mutual forces between the particles, and but it's the same. It just multiplies number of equations, which equals to the number of particles in the universe. But in principle, one could solve these equations, and you see the picture of Earth as a very sophisticated clockwork, which has been set at some initial time, moment of creation of the universe, and then it just, rolls, ticks with a full predictability, and the future is pretty much determined. Good. That was a picture of classical mechanics, typical for, say, 19th century. Then everything has changed, as you know, and we will look at Schrödinger equations soon. But first, let us understand is this equation for what or which object? This is an equation for what is called wave function. Not sure it's a proper wave, proper name, why it's wave, why it's function, and actually it's all confusing. But whatever, let us assume there is a quantity, complex number, which is defined, and each point of the space at all coordinate points, and it evolves in time, and it represents a state of our particle. What strikes us immediately that, all right, it's a number defined in each point of space, in principle, infinite number of numbers, right? And this is instead of 6 numbers, which characterize the state of the particle in classical mechanics. That's very strange news. And there's another strange news. There is no determinism in quantum mechanics. If you measure on classical system, one can arrange measurement in such a way that it's not obtrusive, that it doesn't change the state. Here, the state is necessarily changed when we measure. And the results of measurements are always probabilistic. So quantum mechanics, it is a kind of whatever stochastic science, it deals with probabilities. Well, for instance, to take simplest one, the probability for a particle to be at a certain point, R, is given by square root of the wave function at this point, right? The total probability to be somewhere is 1. It is certain thing. That implies that there is, any wave function must be normalized like this. Right? That's the probability to have a certain coordinate. Right? There must be also a probability to have certain momentum. Perhaps you could think for a while before I give a formula in several slides. What would be the probability of to have a certain momentum for such a particle? Good. So very strange theory, very counterintuitive. Many numbers, but none of them can be measured. Measurement arises information. If you close your eyes, the world will change because you don't observe it. Our intuition, which is based on everyday life, doesn't help us to comprehend quantum mechanics. There are many activities, of such interpretation, of such restructuring of quantum mechanics to make it accessible for our minds. Generally, I do believe that all these complications are not necessary. One doesn't have to interpret quantum mechanics. It's something which is real, which can be experimentally accessible, which can be studied, and which can be comprehended by some work. Initially, it was experimental work, of course, but then tool set has been made. Some tools are 100 years old, some tools are 50 years old, some tools are only 20 years old, with which we can also do something in our mind. I wouldn't even call it theoretical activities, but some exercises which allows you to predict and develop intuitive picture of quantum objects, which in its own turn would allow you to design quantum situations, which would allow you to put it into practice, into quantum technologies. Right? If you ask me, interpretations really are not necessary. It could be nice game of mind, but what is my interpretation platform of the 7 most popular ones? It's interpretation platform of Feynman, which is shut up and compute, shut up and calculate. That might sound pretty theoretical, but it is not. Quantum mechanics, even simplest system, cannot be understood without a little piece of math. without some exercise of your mathematical skills. I must warn you directly that going through our course requires such exercise. Right? You need to refresh your, I wouldn't say even mathematical, it is some art of analytical calculation which you should possess by this time and which you should apply during this course. For some of you, it's natural. For some of you, it's difficult. For some of you, it requires a large effort. And it is good to recognize at which level you are and kind of accept it or do something about this. But that you will figure out soon, presumably already in the first lectures and after first round of homework. Fine. It's again about the course, not about the quantum mechanics. I need to go a bit faster. Right. Let us see Schrödinger equation. Erwin Schrödinger was a kind of well-established, solid German professor when he wrote this equation. Eventually, it was not his ambition. What he wanted is to write an equation for wave function of a relativistic particle. He could not, and okay, it's a kind of big merit of him that he could stop and write the equation for non-relativistic particle, which appears to be much more fundamental and decisive for further progress of quantum mechanics. Good. Let us see what kind of equation it is. First of all, let us notice that this is the same type of equation as for classical mechanics. It's evolution equation. Schrödinger equation predicts time derivative of wave function given its instant moment. Right? So what is this time derivative? It's a wave function upon which the Hamiltonian has been acted. Hamiltonian is here an operator. What does operator do? It grabs wave function, it gives wave function as output. Right? Usual Hamiltonian for one particle contains two terms to represent potential energy and kinetic energy. Potential energy is just multiplication with a number, operator of multiplication with a number. Kinetic energy is a second derivative of the wave function with respect to coordinate. Fine. It's rather complex, but very good news that the question is linear. Quantum mechanics is linear science. Actually, nobody knows why. But well, we don't want to discuss this. We just take it as given. It is a linear equation. Good. What is usually done for stationary Hamiltonian? One considers stationary states of these stationary solutions of the Schrödinger equation. It doesn't mean that they do not depend on time. It means that they depend on time in a very simple fashion. It acquires a phase factor which depends on time and contains a number which appears to be energy. So how do we do this? We substitute this into this equation. And then the resulting equation will be of this type. It will be eigenvalue equation. Any Hamiltonian and operator, it has eigenvalues, and those are discrete energy levels. Quantization of energy, the most important concept of quantum mechanics. It's what the quantum mechanics has been devised for, to explain quantization of energy levels in atoms everywhere. Good. That was Schrödinger equation. All right. That was Schrödinger equation was made by a kind of well-established professor. And very soon, an alternative formulation of quantum mechanics has appeared, made by wow, Jesus, what is going on? Something wrong with my slides. A wrong conversion. Anyway, it was a new formulation which has been put forward by Jan Wald Pearson. I believe Paul Andrei and Maurice Dirac was like 22 at the time, perhaps closer to your age. Right. And what he said, that the wave function is not actually a function. Rather, it's an element of a vector space, Hilbert space. Right, there are two ways to write these vectors, bra or cat, usually associated with wave function and its conjugated value. What is an operator in this situation? What is Hamiltonian? Hamiltonian works in the function and gives a function. Now, instead of functions, we have vector. So the Hamiltonian takes a vector and returns a vector. Such objects are called matrices. So it's in fact matrix. So that's why we talk about Hamiltonian quantum mechanics. Right. So there is a vector. Okay. There is a vector which is obtained by the action of a matrix Hamiltonian on other vector. Good. So the function is a vector. Let us recall what we know about simpler vectors, about say vectors in two-dimensional space. Let me draw a vector array. Vector A can be characterized by two numbers, two components which depend on coordinate system. That's one coordinate system, that's another, and the components like here, two numbers. In a different coordinate system, components are different. So in order to make sense out of these vectors, one needs a coordinate system, at least one. One could, it's actually a matter of our choice, where we can choose it's different, but there must be some coordinate system, which is called in quantum mechanics basis. It is a set of orthonormal vectors. So all vectors are of unit length, and all vectors are orthogonal to each other. Very good. So I guess I have to make a break here. Let's have a break for like 10 minutes, and I will try to fix my PDF. Meanwhile, let me stop from so let me go on. Dirac formulation. Wave function is a vector, like here. Hamiltonian is a matrix. Any operator is a matrix, and in a space we have a coordinate system. We have a basis, and for any wave function, one can define components in different bases. Let me make a step back. Let me talk about physical quantities. In classical mechanics, it's pretty obvious. It's something which we measure, can be coordinate, momentum, whatever, temperature, many things we can measure. We have already seen that the momentum in quantum mechanics has been converted into an operator. It's an operator. Operator has eigenfunctions. And for eigenfunctions, the value of this operator is to be set certain, right? For any operator A, there is an eigenfunction. It acts on this wave function. It just gives you a number, eigenvalue, right? So it's a state of a certain value of this operator. For momentum, eigenfunctions are plane waves. That's why we talk about wave mechanics, but that's a detail. Sure, and kind of one of the postulates of quantum mechanics, one of the, well, all postulates actually come from experimental observation. You assume something, you check it experimentally, you see whether it's good or not. Almost any physical quantity is a Hermitian operator. Not just a number, but an operator, which has a potential to produce different numbers when it acts on the wave function. Right. What is important for us is expectation value of this operator, which is defined with the help of two wave functions. Like we can have a wave function, we can repeat wave function, we can do measurements, and there's some distribution of measurements results, and there's an average of this distribution, which is called expectation value. Let us see what is there in the chat. Yeah, I just, sorry, I have started 2 minutes before the break. Okay, and you haven't missed so much. Very good. So any physical quantity, almost any, is an operator. To give an example of when it doesn't work, say entropy. It's in principle physical quantity, but there is no operator for entropy. But operators are pretty useful, and we will talk a lot about operators in this course. Right, so it's all good in matrix formulations. Let me mention representations. It's just about the same. And a vector, red one, can be represented in green coordinate system or in blue coordinate system. Right? The same with wave function. For any basis, we can define expansion of wave functions over base vectors. These are components. Those are, like with usual vectors, are defined by inner products of the corresponding vectors, corresponding wave functions. Traditional example of representations. One representation we know already, we consider function of coordinates. So it's an expansion over certain set of basis vectors which have certain coordinate. Same with a representation, similar representation is momentum representation. In that case, the basis is the basis of a function of momentum, plane waves. We project, we do this in a product. How we do this in a product? By integration, by sum over all components of the vector, right? So this is in the product, and it gives component of the wave function. So the same wave function can be done in coordinate representation, in momentum representation, and it gives us a lot of freedom. Wave function doesn't care about this freedom, we do, in order to, understand, utilize, predict. Right, very handy representation. Is a representation, is a basis of eigenfunctions of the Hamiltonian. And if you know this representation, or if we knew Hamiltonians are complex, basis vectors are complex, eigenvalues are complex, but suppose we know them, the problem of quantum dynamics is piece of cake. You just expand wave function in this basis and you know everything. It's just a simple it's a superposition of simple stationary solutions of the Hamiltonian equations. All right, so there are different bases, different coordinate systems, different representations. Let me talk about the pictures. If I have time, what should I? No, actually have. What we have just described, it's only one of the ways to deal with quantum mechanics. I'm not talking about understanding, I'm talking about dealing with, right? And this is called Schrödinger picture. Yeah, it's based on Schrödinger equation. And in this case, wave function changes in time, evolves, moves. While operators say just stays the same, operator of momentum stays derivative with respect to r. That's it. Um, However, what matters is not wave function, which we cannot measure anyhow. We can measure only operators. So it's expectation value of an operator which matters. What's expectation value? It's composed of two objects. It involves wave function. It involves the operator. Let's play with the formulas and let us compute time derivative of this operator. Okay, time derivative, it goes to three objects. It gives derivative of the first wave function, second, that's it. But the derivatives are defined by operators. So we could substitute operators here and here. And then what we got for expectation value. It doesn't have time derivatives already. It has an operator which is commutator, so it is product of the two operators taken in opposite orders, right? Which implies that we can have precisely same expectation values if we assume that wave functions do not depend on time, while operators do. This is equation for quantum evolution, which is equivalent to Schrödinger equation, is called Heisenberg equation. And the corresponding way to comprehend what is going on is Heisenberg picture. Right, so operators moving on time. It is new piece of material, but again, if you open your old book with a cat, it's in there. Heisenberg picture. We will use it sometimes. Sometimes it's very, very handy. Working with operators instead of working with wave functions. Let me address rather philosophical questions. Why there are different pictures and why we need them? Well, I'd say because we're humans and we are not single humans, we are members of society. There are different societies. The society we are in is a pluralistic society. So people different views, but somehow, despite all these differences, they can work on the same reality and sometimes even cooperate. Which means, what are your methods? What are your opinions? What is your way to live? Is not matter so much. There are many ways to come to the same result, to solve the same problem. Right, and we can adjust our choices. We can have luxury of choice. We can choose the most convenient for us as for individual or for a group of people. Right, and we can, for any problem, we can choose one or the method which we like. Right, and it's not a wonder that in pluralistic society, theories which are developed allow these multiple interpretations. Eventually, there are not even two opposite pictures like, Democratic and Republican Party in the United States. There's a whole variety of possible pictures in quantum mechanics. One can separate any Hamiltonian into pieces in infinitely many ways, and let one piece to move operators, another piece to move wave functions, and it will be a picture. It will be something you can work with, and for some problems, it's really handy. Right. So I believe it's not a property of reality. It's a property how we perceive reality, how we describe the reality. And the fact that we can have different methods, different pictures to describe the reality is a reflection of our level of development. Like I wouldn't imagine that in truly authoritarian society, people would care about these pictures. They would just learn a single picture and that would be enough, right, for the rest of their lives. But, well, that's not the case. That's the quantum mechanics is like this. Many pictures, many ways to describe the same. And sometimes it has not been, it should not be seen as a nuisance. It should be seen as a freedom. Fine, that was about pictures, and let me go to some tool sets of quantum mechanics. One of the tool sets, which is most widely used and which we also use in our homework and exam, is perturbation theory. What is the problem? What's the hatch? It turns out that only few simple model Hamiltonians can be solved exactly. So we know eigenfunctions, we know bases, we know energy values. And it is very easy to complicate a Hamiltonian, just to add some charm, some new energy, some deformation of potential, which would render it completely unsolvable. Fortunately, we can sort it out. And in perturbation theory, the Hamiltonian is separated into parts. In a simple part, which we know, which we can diagonalize, find all eigenvalues and eigenvectors, and a small part. And this is called perturbation. Oh, right. So how to deal with perturbations? How to incorporate the smallness of this operator M? Well, first of all, we choose, again, it's a freedom of choice. We choose a convenient basis to work with. In this case, it's a basis of original Hamiltonian. And components of the wave functions are written like this. Then we can handle this equation by successive approximation. So first of all, we remove M. That's zeroth order equation, and in this case, CR1 for certain M and zeros for all other M's. Right. Then we consider terms of the first order derivations. Then we can go further. We can consider second order and so on. In principle, one can go infinitely far in these orders, but they become more and more complex. The formulas which I give here are for first order in energy. So first order correction to the energy levels of the Hamiltonian in just expectation value. Let me rewrite it here. That's a first order correction to the eigenvectors proportional to matrix elements of perturbation. It contains also energy differences. And this is second order correction to energy levels in terms of matrix elements of operator M and energy differences. We will use this formula many times, as I promised in the context of homework. Here, just a sketch how to derive it, successive approximations. Right. This is also so that on coming Monday, we will have instructor presentations about refreshing quantum mechanics. There will be more detailed presentation about perturbation theory. That was the question. EM not correspond to H naught, right? So it has index naught, it corresponds to H naught. That's something which we start with zero values of energies in zero order. Then we compute first order corrections and second order corrections, and it goes in parallel with computing corrections to eigenfunctions to coefficient C. But in this equation, both energies and wave function components acquire corrections. Does it answer your question, Sarah? The point is, yes, the point is that H naught is not the perturbation, right? Okay, yes. So Hamiltonian is separated in two parts. One supposed to be simple and big, zeroth order approximation, and this is the perturbation. M is perturbation. Some addition to the Hamiltonian. Very good. So let me go on. If you think I go too fast or too slow, you could also kind of stimulate me in chat. It's perfectly allowed. I would actually appreciate it because sometimes being a complex self-organizing system, sometimes I go too slow, sometimes to go too fast. A little bit of feedback would always be helpful and appreciated. Right. Let me talk about examples, and let me talk a simplest example one can think of. Example of two-level system, and in the modern language, it is called a qubit, kind of elementary quantum unit to store quantum information. What is that about? It's about two states. One can think of a system which consists of only one state, but that system would have any change in dynamics, it would be totally useless and uninteresting. Two possible states. What does it mean? That the wave function, any wave function, is characterized with two complex numbers, alpha and beta. There's also normalization condition imposed, so in fact it's only three numbers. Good. So since wave function has two components, the Hamiltonian has to be, can only be 2 by 2 matrix. Here I put 2 by 2 matrix, has diagonal elements, has non-diagonal elements, and in fact it's arbitrary matrix with 0, 0 trace, so that the reference point of energy is chosen to be 0. Good. Let me have kind of a model corresponding to the system. This is a model of two-level potential. I put a particle here, so in principle there are many levels in this potential, but I will concentrate on the lowermost ones. Then the particle can be either on the left, this is state 0, or on the right. Good. And diagonal energies is the energy difference between the bottoms of the wells. Doesn't matter, epsilon. Good. And there's also tunneling. There's also tunneling through the barrier between these two wells, which is described by a mixing of these functions by non-diagonal matrix elements. Non-diagonal matrix element is generally complex, so T is not equal to T conjugation. But let me restate again that any Hamiltonian is Hermitian operator. It has to be Hermitian, otherwise we would have a terrible problem with the complex energies. Hermiticity guarantees that all energies are real numbers. Fine. So the fact that here we find T conjugated and T here is a hermiticity of the Hamiltonian. Good. So with this Hamiltonian we can compute eigenenergies. Here they are. You just get it from determinant by 2 by 2 matrix. I believe it's a linear algebra, which you followed. And my assertion, 99% of students can compute eigenfunctions, eigenvalues, right? It's mathematical. Eigenvalues of 2 by 2 matrix. But what about eigenfunctions, about eigenvectors of this function? Practice shows that this ability frequently is not present. So please check whether you can do this job. Again, on the session of on Monday, we will talk a little bit more also about this example, about the qubit. Good. So as we come down with two-level system, just to mention that it's also in many presentations which are to choose from. More old-fashioned way to present two-level system is electronic spin in magnetic field. The Hamiltonian is a vector, and it's made of a sigma Pauli matrices like this. So it looks like bz minus bz bx plus ibi Pauli matrices. Oh, fine. So I believe we are done with qubit. We will work with many qubits in our course. Let me go on and let me talk about an oscillator, a harmonic oscillator. There will be many oscillators in this course, really plenty, zillions of them. So let us first train on a simple one. So what is this oscillator? It is a particle with kinetic energy, which is confined in a parabolic potential, right? So if we do it quantum mechanically, the simple linear equations on the momentum and coordinate of this particle, which describe oscillations with a frequency omega. It is what is called linear oscillator, linear system, linear equations, which means that this frequency, for instance, does not depend on the amplitude of oscillations. Right. So what do we see if we solve this problem quantum mechanically? Schrödinger equation is second order differential equation. It can be in principle solved, but it's a rather difficult piece of work. I don't want to describe this now. What is the solution? The solutions are equidistant levels. There is a system of discrete energy levels. In this parabolic potential, this is a ground state. This is first excited state, third, at all. I've sketched wave functions, all wave functions eventually are derivatives of Gaussian functions. This ground state, it doesn't have any node, state with one node, with two nodes are excited states. Right, this is an oscillator. And what I also want to show, again, because it will be useful for the course, I want to show a trick to compute energy levels of this Hamiltonian without writing any differential equations, without even using Schrödinger equation. Let us see. The idea is to introduce, write down such an operator, which looks tricky, but the coefficients here and here are chosen to make our life simpler. Okay, this is not an Hermitian operator, right? It has imaginary unit here, which means that the conjugated operator, it's not the same as A. It is different. Differs, as you can see, in the sign of imaginary part. Very good. What is this? This is transformation from two operators x and p to two operators, A and A dagger. One can revert this transformation. One can express X and P in terms of A and A dagger and put it back to the Hamiltonian. Then the Hamiltonian assumes such a simple form. Good. There's also a commutation relation between these two operators, which is handy. Good. Then there is the following trick. So we assume that we know the some eigen function of this operator with some energy. We don't know this energy yet. Then from this solution, we can form two other wave functions. And substituting this into the Hamiltonian and working out commutation relations, we discover that these wave functions are also eigenfunctions of the Hamiltonians, but with shifted energies. So one operator rises energy, reduces energy, another operator rises energy. Good. So if you start with some energy, you can form levels going up and going down, which is idiotic. All right. That has to since potential is positive, there can be no values at negative energy. So going up is high, is fine, but going out has to be stopped somewhere. How could it be stopped? It could be stopped if I act with this operator on the wave function, it gives me something forbidden, which is not a wave function. The only forbidden vector is zero vector. Zero vector cannot be normalized, is not a wave function. So from this way, I can conclude that there is some special state of this oscillator, which is called vacuum state, which is ground state, and I can even compute its energy. So here I've discovered the vacuum. And then one can use this operator which rises energy and discover equidistant levels. Good. So there's a trick. We will implement this, and it requires some operator algebra. We will also exercise this. Let me see. I think I still have like 15 minutes. There was a question. What about time-dependent perturbation theory? Time-dependent perturbation theory is important in quantum mechanics. We will have some presentations about this, but since we are working with stationary methods, in this course, we will have very little about time-dependent perturbation theory, except several presentations. So at the moment, one can leave and go through the course without time-dependent perturbation theory. Sebas, does that answer your question? Very good. So that was about harmonic oscillator, about operator trick, and let me talk about density matrix. So far we have wave function. It appears to be that there's another way to describe quantum mechanics, which kind of more general, more powerful, you may say so, than the wave function concept. And it is called density matrix. As many physical terms, it's not really self-explained. I would not even dare to say what is the density in this density matrix. I could perhaps devise some interpretation, but it would be like interpreting quantum mechanics. It's an object which is called density matrix. And it comes in quantum mechanics in two facets. Although the concept is essentially the same. First concept is the concept of statistical ensemble. Suppose we have 10 particles and the 5 of them are in a state of spin which is perpendicular to that axis. And 5 of them are in a state which is perpendicular to x. And then we just take arbitrary particle of this 10. We don't know which wave function it has. But we know its density matrix, not just the density matrix which of the particle graph, but the density matrix of the whole ensemble. So this ensemble can be represented as with the help of density matrix. Density matrix, in fact, can be seen as an operator. It consists of two wave functions, and these wave functions are taken with probability of their appearance in ensemble. So instead of a vector, we have a matrix to characterize quantum state of the system. All right, that's first facet. It's ensemble of identical particles. Not necessarily identical, but big ensemble of particles. And it's a concept which naturally comes in thermodynamics. Another concept is a concept of partial trace. I will write it in a little bit abstract level. Perhaps I can elaborate on Monday. Partial trace is useful when all the variables which we have in the system can be separated into blocks. The whole space, Hilbert space, can be separated into blocks. Here, for instance, there's a particle which is in two coordinate space, x and y. So x and y will be these two blocks. Right. Good. We can write full pure density matrix in this basis. That's what I do here. And as a matrix, it will depend on x and y of this function, x and y of this function. It's too much variables. Look, when we're dealing with physics, For instance, if we want to describe air in my room, or in your room, right? There's plenty of degrees of freedom which we might take into consideration. Coordinates of all molecules, their velocities in the whole room. In physics, we are frequently in the situation when we do not want to know about this multitude, that we want to reduce our understanding of the system to few variables. Or for instance, for this function, for this system, we could try to forget about y, right? This operation of forgetting is called in quantum mechanics partial trace. So in fact, I trace over one subsystem, okay, that y was x. I trace over x and I get density matrix which depends on I only. It's not a pure state. One cannot represent this quantum information in terms of wave function, but density matrix will do. Let me outline basic properties of density matrix. First of all, normalization. Since it's made of wave functions like this, each wave function is normalized. The trace of density matrix is just one. Expectation value is, as we just repeated, as we just refreshed, is very important quantum mechanics. Density matrix gives expectation value for you. Just trace of operator R and density matrix itself. Why is it so? Well, it is psi times psi. This psi goes here, so we have usual formula for expectation value. Right. Density matrix can describe pure states, which can be described by wave functions, or more complex states. This is purity criterion. For pure states, squared of this wave function, density matrix just equals to wave function itself. One can introduce a criterion of purity to characterize density matrix. Right, so just this trace of the squared, it can take some values between 0 and 1 being the purity. Good. I've mentioned that entropy is not a physical quantity, right? It's not a physical quantity in quantum mechanical sense. It cannot be presented as an operator. But still, entropy is a quantity which can be computed for many identical systems when you have a possibility to reproduce wave function and measure it again and again, completely characterize it. Right. In this case, entropy can be expressed in terms of density matrix. But see, it doesn't work like operator. That could have been a logarithm of density matrix, but it depends on density matrix itself. It doesn't work as usual. Good. What is last thing to mention about density matrix is that we can compute density matrix in the very same way as we can compute wave functions with the help of evolution equations, right? Just by utilizing, Schrödinger equation, one can prove that dynamics of density matrix is given by this equation. It looks like Heisenberg one. but if you look carefully, it is not. It's an equation for density matrix. Very good. So I've been talking about medicines. Let me finish with some, or for this slide, I don't have take-home messages. Oh, that was a problem with conversion. Let me just try to jump quickly. If I can. Oh, sorry, I can't find a good slide. Anyway, I will upload it. Okay, the problem was that I took a new PDF converter, and that did not work, as you have seen. Let me formulate take-home messages just by my voice. Quantum mechanics is not to comprehend. It's something to work on. Can be done experimentally. In our course, we don't have experiments, but we have to work on. So it requires some simple math exercises, derivations, formulating problems, solving problems. So our math goals will be exercised. So please be ready for that. And this is, it's the way to understand quantum mechanics. We start with simple systems. We look at this, the reality which is there it cannot be intuitively understood, but it can be understood with the help of equations. Right. Two simple systems we looked at, most fundamental systems, two-level system, the oscillator we will encounter many times in our course. You know, the third system becomes an atom, a hydrogen atom. We also touch it a bit, but well, as you see, I don't talk about this. What is yet to take home? No, I guess I'm done. Good, sir. Thank you for your attention. I guess you need to go to the next class. I will stop the recording.